Okay, we are going to look at another example where we use the information from the function first derivative and second derivative to determine some things about the graph and sketch a graph. In a previous video, we did all this before. We took the original function and thought about the domain. So this one has a denominator that is 0 when x is plus or minus 1. So I've excluded those values from the negative infinity to infinity interval. So these are the three intervals left for the domain. We found the first derivative, which required some quotient rule, and then simplified. And so this was our simplified version of that first derivative. We looked at where the first derivative is equal to 0, and we got x equals 0. That's a critical point or critical value, perhaps you call it that. We also thought about where the first derivative does not exist. The only places where the first derivative would not exist are at x equals plus or minus 1. Because those values are not in the domain, they're not actually critical values. But they are values that we want to think about when we set up our sign chart and think about that. So we made a sign chart. I put on there any critical values and then any breaks in the domain. I put vertical lines, dashed lines at those breaks in the domain to remind myself that those are, if you remember from algebra, the location of some vertical asymptotes from this function. And then I checked the sign of the first derivative to determine where the first derivative was positive or negative. And that told me where the function was increasing or decreasing. So the point where it switches from increasing to decreasing is going to be a peak or a local maximum point. So that's what we did before. We're going to focus in this video on the information we can get from the second derivative and then put it all together to think about a graph. All right, so one of the things that's hard about these problems is that in order to find the second derivative correctly, you have to have found the first derivative correctly and simplified it correctly. So we did that algebra in the last video. So now I'm going to find the second derivative from this simplified version of my first derivative. The other thing that's important about these problems too is making sure you label things, right? So I have a first derivative and a second derivative and an original function, and I'm going to use different pieces of that to determine different information. So you want to make sure that you've labeled them and not just have like the right-hand side kind of floating around but not clear about which part is which. So at this step, I need to find my first derivative so I can find my second derivative. So I'm zeroed in on this with it labeled so I can find it. All right, so quotient rule. So I'm going to take the derivative of the top, or derivative of the first function. So derivative of negative 2x is negative 2 times the second function, so times the denominator here, minus the top. So I'll have minus negative 2x. I'm going to go ahead and make that minus a negative as plus. You could do that in a later step here, but minus the top, the first function, times the derivative of the second. And when I take the derivative of that denominator, it's going to require some chain rule. So derivative of the outer part, I'll bring down that 2 and subtract 1. So that'll be to the first power, and then times the derivative of what's inside that function. So 2x times, not minus, 2x. All right, so all this part is from the derivative of the denominator all over the denominator squared. So the denominator is already squared. When I square that again, I'll multiply those exponents. So I'll have x squared minus 1 to the 4th power. All right, so there's my second derivative. Now comes the fun or not so fun part, depending on how you view it. We're going to simplify this, and so that's going to hopefully involve some cancellation. The not so fun part is when students cancel things incorrectly, and then everything after that's going to be messed up. All right, so I want to pay attention to where I have addition and subtraction signs on the numerator here. So I have this negative 2 times this quantity, so that's all one thing, all one giant term, and then plus, and then everything after that is all times each other. So the first step I'm going to do in simplifying the algebra is I'm just going to clean up all of this part that is all one big giant term. I don't need this first power here. But I have a 2x times a 2 times a 2x. So 2 times 2 times 2 is 8, and x times x is x squared. So I'm going to write that last part, everything I've circled there, as plus 8x squared times the quantity x squared minus 1. All right, the danger here is that students want to cross out these x squared minus 1s, and there is some cancellation that happens, but you have to be careful about that. this x squared minus 1 to the 4th power is the denominator of this whole first part and of this whole second part that's after the plus sign here. So we've talked about simplifying that in a couple of different ways. One is I can factor something out and cancel that with the denominator, something on the denominator that is matching factors. The second way is I can treat this denominator as one big term and I can split. So I'll have this whole thing over x squared minus 1 to the 4th and then plus this whole thing over x squared minus 1 to the 4th. Either way, as long as what you do after that is correct, either way is okay. I'm going to choose to factor out an x squared minus 1 factor out of the numerator. So there are other ways to do this. Okay, so I'm going to notice that in everything that I have before this plus sign and everything I have after this plus sign, there's a common x squared minus 1 factor. There's also a common 2 that I could factor out if I want, but my whole point of factoring things out is so that I can cancel. So I'm going to notice that there's no 2 here in the denominator I would be able to cancel with, so I'm not going to worry about factoring that out. Okay, so I'm factoring this out, and then I'm going to be left with a whole bunch of stuff here. So I'm going to use some brackets to sort of group things and keep things separate. So out of this entire first group here that has the minus 2 times x squared minus 1, the quantity squared, I'm factoring out one of those factors of x squared minus 1. So I'll be left with the minus 2 and the other x squared minus 1 factor, right? When I have this factor squared, it means that thing times itself. So I've factored out one of them. I'm left with the other one, x squared minus 1 to the 1st if you want, or I'll just write it like that. Okay, so that was taking the x squared minus 1 factor, one of them, out of this. And then I'll have plus, and then treating the second part as one giant term. When I factor out the x squared minus 1, I'm left with 8x squared. And the whole point of doing that was that I have a common factor that I have factored out that I can then hopefully cancel with something in the denominator. If I couldn't cancel anything, then it may or may not be worth it to factor things out. So I'm canceling that one with one of the x squared minus 1 factors in the denominator. So there are 4 of them times each other in the denominator. That'll leave 3 of them in the denominator. Okay, so that helps because now the numerator will be simpler than it was to start with. I could write more steps here. I'm going to save space, just kind of do this in one step here. But on the numerator, this will be gone. And I do have, notice that you'll have a couple of x squared terms here. I'll have minus 2x squared plus an 8x squared. So I would go ahead and distribute that through and combine those like terms. So a negative 2x squared plus an 8x squared is a 6x squared. If you know you would mess that up by combining that in one step, do it in 2 separate steps. I also have a negative 2 times a negative 1, so that'll be a plus 2. All right, so I distributed through and combined like terms on the numerator. On the denominator, I'm left with the x squared minus 1, the quantity cubed. All right, so there is a simplified version of my second derivative. All right, so that was a lot of work. The harder problems when you've got rational functions or fraction exponents or product rule or whatever, sometimes this is the most work in the whole problem, is simplifying your derivatives. Okay, but now that I've got that, the simplified version of my second derivative, and again, make sure it's clear that that's labeled so that when you come back to it, you can find what you're looking at here. So either a stack of equal signs where it's labeled, or maybe you put right here that is your second derivative. Sometimes I'll even circle it in my work so that I can come back and find it later. All right, but then from there, we're going to do the same thing that we did with the first derivative to find the information from the second derivative. So I'm going to find my hypercritical points. By looking at where the second derivative is equal to 0 and where it does not exist. And need to make sure that the values are in the domain of the function. So I'm going to start by thinking about where that second derivative is equal to 0. So I'm going to set 0 equal to this second derivative. And sometimes students get a little bit overwhelmed by an equation that looks like this, where you have a fraction and it's equal to 0. But because it's an equation where I have 2 sides that are equal, you can actually clear the fractions by multiplying through by that common denominator. I couldn't have multiplied by a denominator up here unless I also multiplied this side, which I didn't want. We just want f double prime equals. So once you have an equation where you have two sides, then you can multiply through by a denominator or square both sides or do different things to both sides of the equation. All right, so if I multiply through by that common denominator, which is x squared minus 1 the quantity cubed, and I'm multiplying through the equation, or another way to think about that is you're multiplying both sides of the equation by that, then that's nice because on the left side, whatever I have here times 0 is still going to be 0. And on the right side, well, part of the reason I multiplied through by that was to make those cancel. You can think about this as x squared minus 1 the quantity cubed over 1. And think about multiplying across and canceling those common factors, or realize that that's why you multiplied through by that, to make that cancel. So you're just going to be left with 6x squared plus 2. Okay, so then at that point, the algebra is going to be different every time. You've got to go ahead and solve for x. So let's go up here and do that. All right, so some of you maybe can look at this and think carefully about what values of x would make that true and know what's going to happen here. But if not, you let the algebra help you. All right, so I need to solve for x. This is quadratic, so I could use quadratic formula or factoring. Or I might notice here that I just have an x squared term, so I just need to isolate the x squared. So if I subtract 2 and divide through by 6, I can do that. So I have negative 1/3 is x squared. And then to solve for x, you would square root both sides. Don't forget a plus or minus. And if you didn't realize it before, then at this step, you should realize that there are no real values of x that make this derivative equal to 0. Sometimes that happens and sometimes it doesn't. The issue here is that I have the square root of a negative number. Square root of a negative number is an imaginary number, which is a number. And sometimes it has uses, but in the context of thinking about functions and graphs and intervals from negative infinity to infinity, those are real numbers. So square root of a negative is an imaginary number, which means there are no real values of x for this one, for which our second derivative is 0. So no hypercritical points that are in the domain of the function. No I'll just abbreviate that, hypercritical values from setting that second derivative equal to 0. So sometimes you get an equation here that doesn't have any real solutions, and in that case you don't have any from that. The other thing to think about for hypercritical points, you want to think about where your second derivative is 0, and you also want to think about where the second derivative does not exist. Okay, so this is where I want to go back and find my second derivative. I might notice that that denominator is 0 when x is equal to plus or minus 1. The derivative does not exist when the denominator is 0. Those are not actually in the domain of the function, though, so they're not really hypercritical values. Hypercritical values or critical values have to be in the domain of the function. So I actually have no hypercritical values from either setting that second derivative equal to 0 or where the derivative does not exist. All right, so the next thing that we did before was after we found critical points from our first derivative, we did have some there, we made a sign chart. And I put on the sign chart the critical points at 0 and then any other breaks in the domain. So for this one, we don't have any hypercritical values or hypercritical points, but I do have some breaks in the domain that I found from before when we thought about the domain of the function. So I'm going to go ahead and make a sign chart. This is a sign chart for this second derivative. I'm going to put on there the breaks in the domain. I'm going to put some dashed lines there to remind me that I actually have vertical asymptotes on the graph of the function at those values, not points on the graph of the function. But what I want to check is the sign of the second derivative. So here's where I want to go back to the second derivative that I had from before. Hopefully I've got that labeled, the simplified version. And I just want to check the sign of the second derivative in each of these regions. So when x is bigger than 1, so say x equals 2. You might notice here, because of the square and the plus on the numerator, that the numerator is always going to be positive, no matter what you put in for x, because you're squaring it and then multiplying by something positive and then adding something positive. The numerator is always going to be positive. So it's really only the denominator that's going to be different signs when x is different values. So I can check both, but I'm just going to worry about the denominator. So when I put in an x bigger than 1, like x equals 2, I'll have positive on the numerator, and then the denominator will be 2 squared minus 1 is 3, cubed, that's 3, so the second derivative will be positive. Between negative 1 and 1, like at x equals 0, is a good one to plug in. Be careful here, the numerator will be positive, but 0 minus 1 is negative 1, cubed is negative 1. So second derivative will be negative in that region. And then something left of negative 1, like negative 2. Be careful, again, when you square. So negative 2 squared is 4. So when I put in negative 2, I'll have 4 minus 1, which is 3 cubed. That'll be positive, and numerator is always positive. So second derivative is positive. So again, remember that the second derivative doesn't tell you about increasing and decreasing. It tells you about happy faces and sad faces, concave up and concave down. So our function is concave up in this region, concave down in that region, and concave up in that region. The original function is. All right, so in your homework, they're going to ask you for intervals where the function is concave up, concave down, and then inflection points would be points where the graph changes concavity. I do have places where the graph changes concavity, but those are not actually points on the graph. They are asymptotes. All right, so in terms of thinking about answering the question, I'll just squeeze that in here. This function is concave up on, we have two different intervals here, left of negative 1, so negative infinity to negative 1, and then this region that is right of positive 1. So that union symbol, or you can just put a comma on something that's written. The online homework will want a union symbol. Concave down on the interval between negative 1 and 1. And I have no inflection points. Okay, so thinking about graphing this function, you can of course use a calculator to help you, but you should be able to use the information that's here and then verify from your calculator that you're getting the same thing. All right, so I usually start when I'm graphing it by graphing any important points, inflection points or maximum or minimum points. I only really have one of those here. So at 0, 0 is a point. I know that's going to be a max, so that should be at the peak of a hill on that function, a local maximum. I have vertical asymptotes at x equals 1 and negative 1. That's remembering something from algebra class. So you would see those on a graph of your calculator if you didn't remember that. But vertical asymptotes at x equals 1 and negative 1. So vertical asymptotes. Maybe you remember some things about horizontal asymptotes. You can also think about what happens when x is large, so you're really using limit values. This function has a horizontal asymptote at y equals 1. You can also plug in big values for x, and you might think about that when you plug in big values for x, the numerator is x squared and the denominator is approximately x squared. The minus 1 has almost no effect when x is really large, so the function is approximately x squared over x squared, or 1. So you have a horizontal asymptote at y equals 1. And then I can go ahead and sketch in this other information. I'm going to do the part between negative 1 and 1 first. So you could do really whichever region you want first. But between negative 1 and 1, I know that the function is increasing and then decreasing, and that this point at 0, 0 should be at the top of a hill, a max. And I also know that between negative 1 and 1, the graph is concave down, so like a sad face. So sad face. And it can't cross these vertical asymptotes. The function's not defined there. Okay, and then on the regions on the ends, so right of 1 and left of negative 1. So I'm going to focus on this region that is right of 1. I know that the function is going downhill. It's decreasing. This information tells me it's concave up, so cupped upwards like a happy face. But it can't be an entire happy face, because that would mean that the graph turns back to increasing. So putting these two pieces of information together, knowing that it's always decreasing in that region and that it's concave up, the only way it can be decreasing and concave up is if it's just part of that happy face, sort of the one side of the happy face. So I know it's going to be this sort of shape of the graph in this region. And I know I have these asymptotes here, and so again, you can use a calculator to help you, but it's going to have to approach those two asymptotes. You could plot some other points also if you wanted, either from a calculator or by hand if you wanted to plug in some other numbers like x equals 2. Okay, same thing on the left side of x equals -1. I know on the left side of x equals -1 the function is increasing, so it should be going uphill as you read that graph left to right, uphill. I know it's also concave up, so like a happy face, but it can't be a whole happy face, because if it was a whole happy face it would be decreasing and then increasing. So it needs to be increasing and concave up. So again, really only half of that happy face, the part where it would be going uphill and cupped upwards. So like this over here. All right, so there's a lot here. These are long problems. So just take your time. Please check if you're having trouble with anything, if you're not sure why you're getting them wrong. I would ask someone to check your first derivative. Do you have that correct? Because if you don't have your first derivative correct, you can't get your second derivative correct. So maybe ask someone to check your work. Ask me if you're in my class. Send me a picture of your homework and I can say, yes, your work all looks correct. You just got the signs wrong or whatever it might be. But there's a lot to these problems. So hang in there and just get some feedback at different steps on it and you'll get it, I'm sure.